Good morning, good afternoon, good evening. This is Professor T. Freed Muhammad, the lecture series of PhD AI 830 for University of the Commonwealth at Kentucky. This lecture is about natural language processing, and we'll deep dive into this together. So the NLP, or natural language processing, is a branch of artificial intelligence that teaches computers to read, understand, and generate human language. It sits at the intersection of linguistics, computer science, and machine learning, and it powers many tools people use every day without realizing it. NLP is not a single technique, but a collection of methods that work together. You need models to understand word meanings, parsers to understand sentences and the structures of the sentences, and semantic systems to understand what a sentence actually means. This lecture walks through each of those layers in order. When you ask your phone, "What is the weather like tomorrow?" NLP breaks that sentence into words, figures out it is a question, identifies weather and tomorrow as the key concepts, and sends the right query to a weather service. The answer that comes back is the formatted response for you by the NLP, and it reads you aloud that answer that it gets. This lecture is organized into 4 chapters for the sake of this lecture, or 4 sections that build on each other. Language models come first because they are the foundation. Without a way to represent and predict language, none of the other techniques are possible. Parsing and semantics come next and go deeper into structure and meaning. Applications come last because they combine everything from earlier discussions. By the end, you will see how the same ideas power tools as different as grammar checkers, Google Translate, and ChatGPT, or Anthropic Claude, or Google Gemini. Think of learning to cook. You first learn ingredients, language models, then how to combine them into dishes, parsing and semantics, and finally, you cook complete meals for people, applications. Each step depends on the one before it. So, a language model is a system that assigns probabilities to sequences of words. It answers the question, how likely is this sequence of words to appear in natural language? This turns out to be an extremely useful thing to be able to compute. Language models are the core building blocks of almost every modern NLP system. Whether you are doing translation, autocomplete, or chatbot conversations, there is a language model underneath making predictions about what words should come next. Your phone keyboard suggests the next word as you type. After you type, "I want to," it might suggest eat, go, or see. Those suggestions come from the language model trained on millions of messages that calculate which words most commonly follow "I want to." The bag of words model represents a piece of text as a collection of word counts. You count how many times each word appears and ignore the order entirely. The result is simple numerical representation that a computer can process easily. Despite being simple, bag of words is surprisingly effective for many tasks. Spam filters, topic classifiers, and document search all work well with it. The reason is that the words present in a document often carry enough information to categorize it even without knowing their order. A spam filter looks at an email, sees the words free, winner, claim, and prize. Appearing many times, it does not care what order they are in. The high counts of those words alone are enough to flag the email as spam. Bag of Words captures exactly this kind of signal. An n-gram is a sequence of n words taken from a text. A bigram is two words, a trigram is three words. N-gram language models predict next word by looking at the previous n minus 1 words. The prediction is based on how often word sequences appeared in the training data. N-gram models are fast, simple, and very interpretable. You can look inside them and see exactly what probabilities they learned. They were the dominant approach to language modeling for decades before neural networks took over, and they are still used in lightweight applications today. Your phone's autocomplete uses n-gram statistics. After you have typed happy birth, the model knows that day follows happy birth in the vast majority of cases. In its training data, it suggests day with very high confidence because trigram happy birthday is extremely common. If a word pair never appeared in the training data, a basic n-gram model assigns it a probability of 0. This is a serious problem because any text you apply the model to will contain new combinations of words, and a 0 probability breaks the entire calculation. Smoothing solves this by redistributing some probability mass to unseen events. The simplest version, called add minus 1 or Laplace smoothing. Add 1 to every word count before computing probabilities. More advanced methods like Kneser, Knee are smarter about how they redistribute the mass of work, much better in practice. So, no smoothing, probability of a Galaxy phone is equal to 0, breaks on any new phrase. Add 1 smoothing, add 1 to every count, simple but over smooths. Kneser, state of the art, used in production NLP. A model trained on news articles has never seen the phrase Galaxy smartphone review because that phone did not exist yet. Without smoothing, the model gives this phrase a probability of 0 and cannot process it at all. And add 1 smoothing, each word still gets a small non-zero probability, and the model can handle the new phrase gracefully. Word embeddings represent each word as a point in a high dimensional space. Words with similar meanings end up closer together in that space. This is a much richer representation than simple word counts because it captures relationships between words rather than just their presence or absence. The most famous example of what embeddings learn is the analogy king minus man plus woman equals queen. The embedding space organizes words so that gender relationships, country capital relationships, and verb tenses all form consistent geometric patterns. Embeddings trained on large corpora carry enormous amounts of word knowledge backed into their numbers. Example, you download a pre-trained glove embedding and ask it for words similar to doctor. It returns physician, surgeon, nurse, and hospital. It does this because Those words appear in similar contract contexts across millions of sentences in the training text. No human labeled these relationships. The model discovered them automatically. So semantic neighborhood would be Paris is to France as Tokyo is to Japan. Walk is to walked and run is to run. And again, run never has ed in the end of the day. So that's a good idea to look into. The foundation of modern NLP is BERT, GPT, and all use embeddings. This code you can test run by yourself in Python. Part of speech tagging is also known as POS tagging. Labels every word in a sentence with its grammatical role, nouns, verbs, adjectives, adverbs, and determines each get their own tag. This seems simple, but it is crucial first step for almost every downstream NLP task. Modern taggers use neural networks and reach around 97% accuracy on standard benchmark. The remaining 3% is largely caused by genuinely ambiguous cases where even humans disagree. The output of POS tagger feeds into parsers, named entity recognizers, and many other systems. You give the sentence, "The quick brown fox jumps over the lazy dog." To a POS tagger, it labels the and the as determiners, so capital T and the small t or the caps T or the lower t for the as determiners, quick, brown, and lazy as adjectives, fox and dog as nouns, and jumps as a verb. A grammar checker then uses these tags to check whether the sentence follows the rules of English grammar. Parsing is the process of analyzing a sentence to find its grammatical structure, where POS tagging labels individual words. Parsing finds how word groups or words group together into phrases and how phrases combine into a complete sentence. The result is a tree structure. Parsing is important because meaning often depends on structure. Two sentences can contain the same words but have completely different meanings depending on how those words are grouped. A parser makes the structure explicit so that downstream systems can use it. Consider old man and woman. Does this mean old men and women of any age or old men and old women? A parser tries to determine which grouping the speaker intended. Getting this wrong leads to misunderstanding the meaning of the entire sentence. So these are the context-free grammars that we are going to discuss on top of the parsing that I just have discussed in quite detail. A context-free grammar is a formal set of rules that defines which sentences are grammatically valid. Each rule says that one symbol can be replaced by a sequence of other symbols. A small set of rules can generate an enormous number of valid sentences. Context-free grammars are used in compilers, in natural language processing parsers, and in chatbot intent detection systems. They give you a precise, checkable definition of what counts as a valid input. When a sentence matches the grammar, you also get its structure for free as a byproduct of the matching process. A flight booking chatbot uses a semantic grammar that includes rules like booking goes to book a flight followed by destination, destination goes to followed by a city name. When a user says book a flight to London, the grammar matches that. The chatbot immediately knows the user wants to book a flight, and the destination is London. A syntax tree shows the hierarchical structure of a sentence. The sentence sits at the top. Below it are the major phrases like noun phrase and verb phrase. Below those are the individual words. Each level of the tree captures a layer of grammatical structure. Algorithms like CYK and early parsers build these trees efficiently. CYK uses dynamic programming, so it's n cube. It's dynamic programming approach. Just FYI, so you know that what I'm speaking. So the CYK and the early parsers build these trees efficiently. This is a profound statement. I thought to repeat it. CYK uses dynamic programming and runs in a cubic time relative to the length of the sentence. These algorithms are guaranteed to find all valid parses if any exist, which is important because many sentences are genuinely ambiguous. Take the sentence, the dog chased the cat. The parser builds a tree with S at the top. S splits into noun phrase, the dog, and the verb phrase, chase the cat. The verb phrase splits into the verb, chased, and another noun phrase, the cat. This tree structure tells you who did what to whom, which is essential for understanding the sentence. Dependency parsing. Dependency parsing is a different way to represent sentence structure. Instead of grouping words into nested phrases, it draws direct links between individual words, showing which word depends on which other words. Each word points to its governor, the word it is grammatically attached to. Dependency parsing is popular for many languages because it handles word order variation more naturally than phrase structure parsing. Many languages allow much freer word order than English, and dependency relations stay the same even when the word order changes. Tools like Spacy use dependency parsing as their primary structural representation. In a sentence, she gave him a gift. Dependency parsing shows that gave is the root, she is the subject, and gave him is the indirect object. The gift is a direct object. This immediately tells you the roles of all participants in the event, which is exactly what you need for information extraction. Semantics is the study of meaning. Syntax tells you whether a sentence is grammatically well formed. Semantics tells you what the sentence actually means. These are separate questions, and both matter for building systems that truly understand language. Computational semantics try to represent meaning in the form that computers can reason with. If you can translate a natural language sentence into a formal logical representation, you can then use standard reasoning tools to answer questions, verify facts, and draw inferences. This is the foundation of question answering system. The sentence, "No student passed every exam," has a clear grammatical structure, but its logical meaning is quite subtle. Semantics gives you the tools to represent exactly what it means using quantifiers and predictors and predicates, and then to check whether the statement is true or false given a database of students and exam results. First order logic is one of the most common ways to represent the meaning of natural language sentences formally. It uses predicates, variables, and quantifiers to capture the relationships between entities that a sentence describes. A sentence like "John loves Mary" becomes the logical form love, John, and Mary. So that's something that I would suggest you look into that by applying some of your Python code that you can write using the given structure in this semantic meaning representation. A voice assistant receives the question, is the Eiffel Tower in France? The semantic parser converts this into logical query, is Eiffel Tower, comma, France, and in, and brackets Eiffel Tower, comma, France, bracket closed. The system looks up this fact in its knowledge base, finds it is true, and answers yes. Without romantic or semantic parsing, the system would have no way to match the question to the structured data in the knowledge base. So a system can neither be romantic, can only be semantic. Semantic grammar's user input is book a flight to Paris on Friday. Semantic grammar, book, destination is equal to Paris, day is equal to Friday. Action, query flights, destination is equal to CDG, date is FRI. Another example is a bank customer service system uses semantic grammar. When the customer says transfer $200 from my savings to my checking account, a grammar parser parses this and produces a structured action. Transfer amount is equal to 200, source is equal to savings, target is equal to checking. The banking software then executes this action directly. There is no ambiguity and no guessing involved in this case. The sentence I saw her duck is structurally ambiguous. It can mean you witnessed a woman crouch down or you saw a duck that belongs to her. As a human reader, you probably noticed both readings immediately. An NLP system needs to consider both, gather context from surrounding sentences, and pick the more likely interpretation. Getting this wrong changes the meaning of the entire message. So I went to the bank. Reading is a riverbank financial institution. Context, deposit money, resolves it. Human NLP handles this effortlessly using surrounding context and word knowledge. Machines find this very hard. That's a lexical ambiguity. Structural ambiguity is she saw the man with binoculars. Readings, she used binoculars to see him. He had binoculars. Requires word knowledge to resolve. Human NLP handles this effortlessly using surroundings context and word knowledge. Machines find it very hard. So both lexical ambiguity and structural ambiguity can cost the meaning different, or I saw her duck is also the similar example. This discussion, or chapter 4 in this lecture, which should have been section 4 or part 4, shows how all techniques from earlier in the lecture come together in the real products that people use. Language models, parsers, and semantic systems do not exist in isolation. They are combined into pipelines that take raw user input and produce useful outputs. A customer service platform for an e-commerce company uses all 4 applications. It translates messages from international customers, analyzes the sentiment of each message to prioritize angry customers, answers common questions automatically, and routes complex cases to a human agent after summarizing the conversation. NLP makes all of this possible at scale. A retail company launches a new product and uses sentiment analysis to monitor Twitter in real time or X in real time. Within hours of launch, the system detects a spike in negative sentiment about the product's battery life. The company's system or company's team is alerted automatically and can respond before the issue becomes a major public relation problem. Without NLP, this would require dozens of people reading thousands of tweets manually. So, machine translation, sentiment analysis, question answering, chatbots, and assistants. The examples are given on the screen. Transformers and attention. You type the bank by the river flooded into a transformer based system. When processing the word bank, the self attention mechanism assigns a high weight to the words river and flooded nearby. This tells the model that bank here means the edge of the river, not the financial institution. An older model that processed words left to right one at a time would struggle much more with this disambiguation, and the transformer and attention is part of the scale methods. GPT-4 has 1 trillion parameters, give or take. Attention is quadratic in sequence length. The active research frontier is making it linear so we can use longer context affordably. The animal did not cross the street because it was too tired. What does it refers to? Attention scores. It goes to animal 0.87. Street is 0.04. 2017 we had Transformers. 2018 we had Bird. 2019 we had GPT-2. 2022 we had ChatGPT. 2023 plus till today is Claude and Gemini and many other things associated. So definitely read Attention is All You Need, the paper written in 2017. Okay, almost the last slide, but not the least. Consider the word bright in 3 sentences. She is a bright student, or he is a bright student. Means he or she is intelligent. The room has a bright light. Means the light is strong. He wore a bright shirt. Means the shirt has a vivid color. A context-aware model like Bird produces a different vector for bright in each of these sentences, capturing the different meaning. A simple word embedding model would produce the same vector every time and miss the distinction entirely. So the Bird was first model to read a word in context of all words around it simultaneously, forward and backward. This bidirectional context was the breakthrough that unlocked near human reading comprehension benchmarks. Every modern LLM inherits this idea. So the word bank, meaning A, river bank, meaning B, financial bank, resolution, rivers versus money. Bright, bright student, bright light. Adjective shifts meaning by noun. I can, ability. Tin can. Syntactic role changes the meanings. These are the key insights in terms of language is context dependent. Okay, language models, transformers, parsing, the big picture, semantics. I would strongly suggest you to look into these things carefully and learn and grow within. So take good care. See you in the next lecture.